तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will discuss the numerical methods adopted for calculating the integral of a function. So, we will be looking at some of the rules, most of the commonly used methods for computing integrals numerically will be discussed in these lectures. So, as you know that we can write the formula for an integral in this form. So, we represent it by a simple I, and we say I of a function f. So, this notation would mean that integral of a function f, and then that is integral let us say one variable f of x dx. Okay, so, we limit our discussion here to an integral of one variable, and within the limits some limits a and b. So, now the thing which we will be discussing is how to compute this integral using numerical methods. So, we will follow procedures to start with procedures similar to what we did for computing the differentials. So, that is approximate the function by a polynomial. So, as you know, most of the time we would need to compute these integrals numerically when we do not know what this function, what the functional form is, that is we have again a set of data points. So, we have a given tabulated data, and then we want to find the integral. Okay, that is most often the case when you will be using this numerical scheme for integration. There will be some cases where the function is so difficult to compute. We know the functional form, but it is difficult to compute, evaluate the integral analytically, and then we will again do that numerically. So, there are some cases where that also must be required. But so, for the time being, we assume that what we have is a set of tabulated data points, and the same method can be applied even when there is a known function, because we can always tabulate a set of data points given a function. Having the function and the value, the tabulated points, at the tabulated points in this form f of xi and xi pair. Okay. Now, we want to evaluate this integral. So, with x being xi is greater than a and less than b. Okay. So, that is what we will be evaluating. So, in that case, we can approximate this function f of x by a polynomial p of order n, right. So, we will say f of x can be approximated by a polynomial p n of x, right, and then we will say that I of f is now can be approximated by I of p n, and then we will write that as integral a to b p n of x dx, okay, plus some error term in this thing. Okay. So, our idea in these lectures would be to evaluate, find an expression for this quantity and also for this quantity, which is the error, for using different schemes. Okay. So, that is what we would be looking at. So, to summarize, the idea is the following, or the basic theme of this lecture is the following, that wherever an analytical expression for the integral of a function cannot be found, given it could be because we do not know the functional form of this, we only have a tabulated set of data points, or you have the functional form, but it is difficult to do the integral analytically. In both cases, it is necessary to use some numerical methods to evaluate integrals. So, we will look at some of these methods to evaluate this integral. Okay, for that, we will first we will formulate a theoretical basis, and then from there on we will look at various schemes which will implement which would allow us to calculate this integral. So, that is the basic idea, and then now as I said that we would approximate, the first thing to do is to always approximate this function f of x by a polynomial of degree k here. Okay, so, less than or equal to k plus p, which we call p k of x. So, that polynomial interpolates the function between through all these points, all this tabulated set of points x 0 to x k between two limits a and b, let us say. Okay, and then we can write the approximation for the integral I of f x by I p k of x. And then there is an error in this approximation, and that error in the approximation is given by this next term in the polynomial. Okay, so, that is the same procedure which we had used earlier. So, remember which we have been using that when you say we had p an approximation for by a polynomial approximation, an approximate polynomial that passes through a set of data points. Okay, if you have k data points and we use a polynomial of order k minus 1, or if you have k plus 1 points and if you use a polynomial of order k, and then the error we can compute as the next term in the polynomial. So, we said that we can write p k as so remember that is f of x 0 plus f of x 0 x 1 into x minus x 0. So, we said that we could write this and then write the last term as f of x 0 x 1 up to x k minus 1. So, that is, and then we will write x minus x 0 into x minus x 1 up to x minus x k minus 1. So, that is a kth order polynomial. And the error in the last term would be that there is the error which I will write as, so this is a kth order polynomial here I have, okay, and then I have the error can be written as of this order, that is f x 0 x k, okay, whatever be the k point. Right? So, I add an additional point x k, okay, and now that is the k plus 1th order polynomial. Okay, so, that I will have as x minus x 0 going up to x minus x k. Okay, that will be my error term, right. So, that is my error term in the polynomial. So, that is what I am trying to write here. Okay. So, in this case I have written a k plus 1 order term. So, there is a kth order polynomial and a k plus 1 order term. So, and the error at x. So, here it is written as, now if I want to evaluate this polynomial at x, I just add this point as, so that is a k minus 1 term, I add one more point here and write this as, sorry, just make a small change. So, x k x k plus 1, and then I would write it as x minus x 0 into x minus x 1 x minus x k, and then plus the error term as f of x 0 x 1 x k plus 1, and then I make the polynomial pass through that particular value of x. So, remember this is my polynomial in the Newton form, and I can evaluate this polynomial at any value x, right. And so, there will be some error. Okay, that error term I can compute by saying that I construct a polynomial that passes through x by putting that, taking that as one of the tabulated value, and then writing pi I going from 1 to n, 1 to k of x minus x I. So that is my error term in the polynomial. So I going from 0 to k. So here's the k minus 1. So that is my error term in the polynomial. Okay. So what I did was I say that to write the error term, I said I can construct this coefficient by demanding that this polynomial goes through x, the value at which I want to evaluate, so that this whole polynomial is exact, and then write that as the error term. Okay. Of course, we have seen that this will be of the order of f k plus 1 derivative, the k plus 1 derivative of the function f divided by k plus 1 factorial. We have seen this earlier, that this will be of this order, this function will be of this order, k plus 1 factorial, and this is what I will write as psi. So this is written as psi k of x. Okay, that's the notation we have used here. Okay. So this quantity is written as psi k of x, which is actually going from 0 to k x minus xj, j going from 0 to k. So that's the polynomial representation of this function with the error term, and all this we have seen earlier in the polynomial case, and again in the when we evaluate the numerical derivatives, and now we are using this for also computing or laying the theoretical foundation for numerical integration, and the only new notation we use here is this quantity psi k, which is product of x minus xj for j going from 0 to k. That is our notation, and that will be the error term. Okay. So when we say the integral I of f, we approximate by integrating I as integrate I pk of x, okay, and then the error term in this would be the integral of this quantity. Right. So the error term in this would be integral a to b of f x0 xk plus 1 into x, and we will say psi k of x. So that will be our error term. Okay, so given that we can write down the error estimate in this form. Now I of f minus I of p of k as this integral. Right. So assuming that this quantity f is continuous and integrable function of x. So that is important. So assuming that this is continuous and integrable in this interval, okay, we can write the error term as that. Okay, so now as I said that we can approximate this quantity by the derivative of the function at a k plus 1 at any point, the k plus 1 derivative of the function f at some point eta between a and b. We have said that this follows from the mean value theorem, and we can use this this approximation for this coefficient. That is, the coefficient can be written as the k plus 1th derivative divided by k plus 1 factorial for some eta in between a and b to evaluate this error. So that's, and then we can write this error term as this quantity, then it will not be a function of x anymore. So we just take this out and then write this as this quantity multiplied by the integral of psi k of x dx. So we can write this error as f k plus f, the k plus 1 derivative of f at eta divided by k plus 1 factorial into integral a to b psi k of x dx. And this is definitely an estimate of the error, provided that, so that is what I am trying to write here. So that this is definitely an estimate of the error, provided that this quantity psi k of x is of one sign, it does not change sign. Okay. So we can show that this is equal to or can be approximated by f k plus 1. By that I mean the derivative of f, the k plus 1 derivative of f at eta, the k plus 1 factorial integral of integral a to b psi k of x dx, okay, provided psi k of x is of one sign, negative or positive, within the limits a and b, and then I can approximate it by this using mean value theorem. Okay, so that is what we will be using. So, you can see that if I do calculate the integral of this function by approximating it by a polynomial of order k like this, and then the error I have is of the order of the k plus 1th derivative of the function multiplied by this integral, provided that psi k of x is of one sign. We will see specific examples of this. So, that is the first lesson we learned here, that is the error can be of this order if psi k, if, please note that if, that psi k of x is of one sign, then I can write this as the k plus 1th derivative divided by k plus 1 factorial. So, that is one method of evaluating or estimating the error, okay, by approximating the function by a polynomial. Now, this need not be always true, that psi k of x need not be of one sign in the whole interval, okay, that depends on what values at what points are the function tabulated in this interval a to b. So, that is, so what happens if what, so can we estimate it in some more general cases? It turns out that there is one more special case in which we can evaluate or we can approximate this error, or we can get an idea about the error. Again, I will say a special case, there is no general case for this. So, one case is where psi k of x is of one sign. Now, another case is where the psi k of x is the integral of that is 0. Okay, there are two special cases which we will be discussing. Okay, so, if psi k of x is of one sign, then as we just now said, I can write this as some function that take this outside, okay, and then replace this by the k plus 1 derivative, right, and write that as f k plus 1 eta by k plus 1 factorial into psi k of x theta. Okay. So, if provided again that f of x is now k plus 1 times continuously differentiable. So, I forgot to tell you this, this is a caveat here again, that f of x is be continuously differentiable in the interval a and b. Then we know the error is of this form, of this order, okay, for some value of eta in between a and b. Okay. So, remember the mean value theorem which is used here to say that this quantity f of x0 x k x can be approximated by, or there is at least one point within the interval a and b which is called, which we call eta, at which this derivative or this function can be approximated by the k plus 1th derivative. That is a mean value theorem. Okay. So, now we look at another case, that is psi k of x is not of the same sign, but integral psi k of x dx is equal to 0. Okay. So, now here we can use slightly a different method, that we could say that, so now psi k of x dx is 0. We want to look at the special case where integral psi k of x dx is 0. That is, we want to write, so remember that we had the approximation for the integral I of f by I of p k, and then we said that the error, if this is of the order of integral a to b of this function f, so the f, this coefficient of the k plus 1th term in the polynomial, which is k0 x0 x k x psi k of x dx, where we said that psi k of x is pi I going from 0 to k x minus xi. So, now what we are saying is that this integral, so we have the special case where psi k of x dx between the limit a to b is 0. So, in that limit can we approximate this error by, in some ways. So we saw that when this psi k of x was of one sign, when psi k of x was of one sign, I could use the mean value theorem and approximate this error. So the second case is where this integral is 0. So then how do we approximate? So then we will use the following property of these coefficients of the Newton's form polynomial, that f of x0 xk plus 1 x can be written as f of x0 xk minus f of x0 xk minus 1, then the last term would be now x. Okay, so it's xk. So we want to write xk plus 1 x, so we will write f of x0 xk and f x0 x divided by x minus xk plus 1. Okay, or in short, I can write f of x0 xk x, okay, as so if I can approximate f of x0 xk into x, this function, from this divided difference scheme. The next order divided difference being the divided difference of the previous order divided difference. Right. So that's what we are using. Remember what we used in the Newton's form to compute, that we said f of x0 x1 x2. This third order is f of x0 x1, so x1 x2 minus f of x0 x1. The second order divided difference is divided by the x0 minus x0. Okay, that's what we had used. So we use the same scheme here. Okay, so and then write the divided differences as in this form. Okay, so I can then write f of x0 xk as xk plus 1 x into x minus xk, and that f of, so what I am writing is f of x0 xk plus 1 x is equal to f of x0 xk x minus f of x0 xk plus 1 divided by x minus xk plus 1. So I am using that scheme to write my new value of f of x0 xk x. So this quantity here I can replace now by a k plus 1th order term. Okay, so now this I can replace this by now f of x0 xk plus 1 x, okay, plus another term. So that's what I want to do here. Okay, so that's this term. Okay, so I'm going to replace my error in the integration, that is by this by this quantity. And then I have so basically I will replace this error here. Okay, now using that theorem, using that divided difference, okay, scheme, I would replace that by this integral here by now integral a to b. I'll say f of x0 x1 xk plus 1 x into x minus xk plus 1. I get an additional term there from the divided difference. Okay, then plus I will have another term which is f of x0 xk plus 1 into, so and then the whole thing multiplied by psi k of x dx. So that's what now I have. Okay, so I have two terms. Okay, now one coming from, so this quantity is going to be replaced by two terms. One is a k plus 1 into x term. This is a new term, and then I have this extra term here. But I know that if I write this as two integrals, okay, I know that this quantity will vanish, okay, because this is not a function of x. Okay. So this will simply become integral a to b f of x0 xk plus 1 times x into x minus xk plus 1 into psi k of x. That is actually psi k plus 1 of x now, right. So psi k of x is already a product up to x minus xk, starting from x minus x0, but now I have another term which is x minus x k plus 1. So, this will become psi k plus 1 of x, and then I have another term into dx plus integral a to b f of x0 x k plus 1 into psi k of x dx. Okay, now, this is a constant, right. So, this psi k of x dx integral is 0, that is a special case we are looking at. So, this term goes to 0, and then we have what is left with is integral a to b f of x0 x k plus 1 now comma x into psi k plus 1 of x dx. So, we started with error being a kth order term, okay, and we ended up with a k plus 1th order term. Okay. So, that is the idea. So, here actually a kth order up to this is k, and here now it becomes k plus 1. Okay. So, we went up. So, if you now if I say that okay, psi k of x integral was 0, but psi I chosen my k plus 1th point in this. Okay, I have added a new point here k plus 1. I chosen this point such that this psi k plus 1 of x, which is now I going from 0 to k plus 1 x minus xi, is of one sign. Okay. So, I had two cases here. So, I had started with the case that integral a to b psi k of x dx is 0. So, now I am saying that I can, because of this property, okay, I could write my error in this form now. Okay. All I have chosen was to add a k plus 1th point into my calculation, okay, and write f of x0 x k x as f of x0 x k plus 1 x into x minus x k plus 1 plus f of x0 x k plus 1 using the divided difference table. I added a new point, okay, and use the divided difference table to write from this one. Okay. So, this function here, this coefficient of the polynomial is replaced by now this, okay. And since integral psi k of x dx is 0, this term goes to 0, and then I have x minus x k plus 1 into psi k x, that becomes psi k plus 1 of x. Now, I am saying that I choose this x k plus 1, k plus x k plus 1, this k plus 1th point, such that this product psi k plus 1 is of one sign. Okay. So, this was 0. Now, I say that psi k plus 1 of x is of one sign, that is either plus or minus throughout the interval a to b. So, in that case, I can again use the mean value theorem and approximate this as f of order k plus 2 derivative divided by k plus 2 factorial, right, okay, at some eta between a and b, integral a to b psi k plus 1 of x dx. Okay, now that is a point. So, by choosing my k plus 1th point cleverly, that is by saying that I choose this k plus 1 point such that psi k plus 1 of x is of one sign, I can write the error of the integral, okay, as of the order k plus 2 derivative, the k plus 2 order derivative. I am not saying the polynomial assumption here, I still have a kth order polynomial, but my error is of k plus 2 order. Okay. So, that is what I am trying to summarize here. Okay. So, I can write that thing, and then since this integral can be, now I can pull this out, right, that is what I have done here. Okay. Now, this is 0, which we know that, and then I can write my error as of k plus 1th order by writing in this fashion. If this is of one sign, again this has to be of one sign, this I k plus 1 here. Okay. If this is of one sign, and then this will become a function which is by mean value theorem something of the order, so k plus 2 derivative. Okay. Provided again that this multiplied by x minus x k plus 1 is k plus 2 times differentiable. Okay. So, then I can write it in this form. Okay, so we have found that there is a case where I have the kth order polynomial approximation to the function, while the error is of the order of the k plus 2 derivative of the function, provided the function is differentiable k plus 2 times within the interval a to b. And I can choose my points such a way that psi k plus 1 of x, that is x minus x 0, the product x minus x I, or I going from 0 to k plus 1, is of 1 sign in this interval. So that is a special case which we have seen. Okay, so now I can generalize this, right? I can say that, okay, I choose my k plus 1th point, okay, such that again integral psi k. So this is a case where, as we said, psi k plus 1 of x is of 1 sign, but I could choose my k plus 1th point such that the product of that is x minus x k plus 1 into psi k of x is also 0. That is, the integral dx of x minus x k plus 1 psi k of x is also 0. So this was 0, but we choose the k plus 1th point such that it is again 0. This integral of this is also 0. And in that case, I can go through the same argument and add a new term there and go to a k plus 2 term. Right. So I can continue this process. Okay. I can, as long as I can come up with points x k plus 1 at which I can tabulate the function such that this integral of this quantity is 0. Okay, I can go to the next term. So this is particularly useful when we actually know the functional form of f of x. If we actually know the functional form of x, then we could tabulate it at some special points, such that this integral is always 0. So if you do that, okay, then the derivative, also the error in this thing can go down to a higher order, to go to higher and higher order derivative of the function. So that's a useful thing to do, and that's what we would use in the quadrature schemes. Okay, this idea has been used in the quadrature scheme. Okay, so for the time being, let's understand this, that I can approximate this integral by a polynomial, and the error in the polynomial approximation, the error in the integration because of the polynomial approximation is of this order, which if psi k of x is a 1 sign between the limits a to b, can be written as the k plus 1th order derivative of the function multiplied by integral psi k of x dx. But in the case where psi k of x dx integral is 0, I can use the divided difference idea and go to and add one more term into this error. Okay, I can split this term into 2 such terms, and then I can see that this integral, this part is 0, so I can write this as a k plus 1th order term, a k plus 2 order term. So k plus 2 order in derivative term. So and then if I can choose more points, then I added here a point x k plus 1, but if the point added was also such that integral a to b psi k plus 1 of x is dx, then I can go to the k plus 2 from k plus 2 to k plus 3 order derivative, etc. Okay. So I can continue this. So I can go from the k plus 2 order derivative to k plus 3 and so on. Right. I can go up to very high accuracy, provided I can actually choose my points and the function is differentiable up to that order. So we will now look at some special cases of integration, and we will evaluate the error using this basic theoretical frame. So we will look at to start with 3 different cases called rectangular, midpoint and trapezoidal rules to integrate a function. Okay, so let's look at a function of this form. Let's say we have a function of this form. I plot that function f of x versus x, and then I have some function of this form. Okay, and now I want to find the, so let's say this is my this is a and that is b. This is x equal to a and this is x equal to b. Now I want to compute the integral of this function. So what does it mean? It means that we want to compute the area under this curve in a one dimensional case, this one. So we just simply have to compute the area under this curve. Okay, so that's what we mean by computing the integral of this function, right? So we can look at various schemes which I call here as a rectangular, midpoint and trapezoidal rules, and we can write down, we can draw the area computed by these rules and see what the error in our calculation is. So a simple function like this would help us understand the error in these schemes. So let us start with a very simple case where we would approximate the function by a polynomial of order k, that is k equal to 0 to start with. Okay. So that is the simplest case. That is what we will be saying is that we will approximate f of x by a polynomial of order 0. Okay. So what does it mean? It means that we will write this as f of x0, right. So at x0 being the one point at which the function is tabulated. Okay. So look at graphically, what does this mean? It means that we are going to say that this whole curve is, we are going to take just one point on this curve, okay, some value x0. We just choose some value x0 and we say that that's the point at which we are going to evaluate the function. Okay. So and then what will be the integral of this function? So I of f between the limits a to b. So we say, okay, so between the limits integral a to b f of p of x, right. So that p of x will be p0 of x dx. So p0 of x is just f of x0, so that is integral a to b f of x0 dx. So that will be simply f of x0 into b minus a. Right, that is what it is. Okay, so we have approximated the integral by a polynomial of order degree 0, that is k equal to 0, which means that the integral would be just f of x0 into b minus a. Right. We approximated the polynomial by the function by a polynomial of order 0, that is the integral by f of x0 into b minus a. Okay. So that now it depends on where we choose the x0 to be. Okay. So if you choose the x0 to be, let us say a, okay, it will become f of a into b minus a, or if you choose f0 to be x0 to be a plus b by 2, then it is x minus a into f of x a plus b by 2 into b minus a, etc. So that's the schemes which you are going to look at. Okay, so let's just choose, let's not choose a to be here, somewhere here. Let's just say a is this. Okay. So now if I choose x0 to be a, and then this is saying that I take the function value at there, okay, so that is my f of a, right, and I am saying that I will take the function value there and multiply it by b minus a. Okay, so what am I getting? I am basically computing the area under this curve, right, so area under this box. Okay, that is what I am going to compute. So I am going to approximate this whole integral area under this thing by area under this box. If I choose my, okay, so I actually have to compute the area under this whole curve starting from here to here. Okay, so I should have computed this whole area. Instead of that, by this scheme I am computing it as the area under this box here. So my error is obviously all this unshaded area here is my error. So that is what we see. Okay, so in this scheme we are just taken to be f of x0. So I choose x0 to be a, okay, and then this approximation becomes simply b of b minus a and f of a, and that's obviously called a rectangular rule because as you see graphically that we are just using a rectangle. Okay, for instead of computing this whole area under this, we just choose a rectangle of this shape here and we compute the area under that. So that's the error, or that's a integral. Okay. So from the polynomial approximation we know the error in this polynomial, in this computation, would be the next term in the integral of the next term in the polynomial, okay, which will be p0 f of the error would be then e would be integral f of x0 x1, right, into x minus x0 dx, correct, because that is the next term in the polynomial. Okay. So that is, we are choosing our new point x1, okay, and you say that f of x0 x1, f x0 x1, this is the coefficient of the next term in the polynomial, into x minus x0 dx. So that is the next term in the polynomial. So the integral of the next term in the polynomial is my error here. Okay, that is what we would look at now. Okay, so I will write that error as that, and now if I choose my x0, I have chosen to my x0 to be a, right, that is what I chosen here. I choose my x0 to be a and said that, so in the case x0 is a, so this integral was f of a into b minus a, and the error would be integral a to b f of a times some point x1 which we have to choose, right, into x minus a dx. Now you see we chosen a to be as the x0, that is we chosen that is one of the limits, right. So all x values are higher than a, okay, because we are going a x starting from a to b. So all x values in this integral are greater than a. So x minus a is always positive. So this quantity which was our psi 0 of x is a 1 sign, it is always greater than 0 for all x values. So it is a 1 sign, so I can pull this out, okay, and I can say that my error here is of the order of f first derivative, right, because 0 is our order, into at some point eta and integral x minus a dx between the limits a to b. That will be my error in this rectangular rule. Okay, so that is what I have tried to write here. Okay. So that is, now I can just integrate x minus a dx, this becomes x minus a whole square by 2 within the limits a to b. So I get my error in this rectangular rule which I call as ER as f prime, that is the first derivative of the function, multiplied by b minus a whole square by 2. Okay, so if you want to get the maximum error, we could approximate this by the maximum value of the derivative in the interval a to b multiplied by b minus a whole square by 2. Okay, so now that is one case of the rectangular rule which we just saw. Okay. So now let us look at, so that is for the rectangular rule, and we call that as ER, okay, to represent it as a rectangular rule. Now in this particular case we have chosen x0 to be a, okay, so that psi 0 of x is greater than 0 throughout the interval, greater than or equal to 0 throughout the interval. Okay, so that is of one sign. So let us choose the next case, that is we choose, we want to now look at the example where this integral would be 0, that is integral psi 0 of x dx is 0, that is psi 0 of x is not a one sign, but integral psi 0 of x dx is 0. So we can choose for that the case x0 equal to a plus b by 2. Okay. So what are we saying that? Okay, we are saying the following, that now we will have the function evaluated at so we take x0 to be a plus b by 2. Okay, so that is the case where, okay, so that is somewhere here, that is my a plus b by 2 point, and that is a function value at that point. Okay, and then I multiply that by a minus b. So my integral now will become, if I choose x0 to be a plus b by 2, okay, my integral I of f, which is approximated by I of p0 of x, will become what we get as integral a to b, right, we will get that as f of a plus b by 2 into dx, and that will be f of a plus b by 2 into b minus a. So that is the area of the box area of this box, that is okay. So now we have a shaded area all the way like this, all the way up to that. Okay, so I have a shaded area now all the way. Sorry, this is not correct. That's my function, and then I evaluated it at this box. Okay, so that is f of a plus b by 2. So that is f of a plus b by 2 multiplied by a minus b. So that will be the area under this shaded curve here. Okay, so that's my next approximation to this function. Okay, and so that's my polynomial. Okay, so it's the same one polynomial of order degree 0, but I choose x0 to be now a plus b by 2, and then I have a different integral approximation, or approximation to the integral. So now I have chosen my x0 to be a plus b by 2. Now look at that. Now we have this integral now here, this psi 0 of x, right? Psi 0 of x now is x minus a plus b by 2 in the limit a to b, and now that's 0. Okay, so now we have to choose a new point x1, okay, such that we can define the error. So that's the second case. The first case was where psi of x had the same sign and the same zeroth order polynomial approximation. We can choose x0 differently. Now we choose the midpoint, that is a plus b by 2, midpoint of the interval, such that the integral of x minus x0 dx is 0. Okay, and then we can now define that error as the next term in the polynomial, also next order term, that is now we will have the second order derivative. Right. So we will have the second order derivative and the b minus a by 2. In the case where we had psi k of x is of one sign, right, is of one sign, okay, and then I said that the error would be of the order, the error in the polynomial, error in the integral will be of the order f k plus 1, that is a derivative, k plus 1 derivative by k plus 1 factorial, right, integral psi k of x dx between the limits a to b. Now we had seen that in this, now we have seen that by choosing x0 to x0 to be a plus b by 2, this integral is 0. So we now choose a new point, k plus 1th point, right, and write this as the next term, right. So we have to make this into one sign. Okay, so now this is not of one sign, but the integral is 0. Now I have to make my psi k plus 1. So I want to write my psi k plus 1 as psi k into x minus x k plus 1, and I want to say that this is of one sign. Okay, so that is, I want to say x minus a plus b by 2. Now I want to multiply it by something else such that that is of one sign throughout the interval. Okay, so that's x minus x k plus 1 is of one sign throughout the interval, and that I choose to be x0 itself. Okay, so that is, we will just choose this x k plus 1 to be again a plus b by 2. So we will choose, okay, we will choose x k plus 1 to be a plus b by 2 again, such that our psi k plus 1 is now x minus a plus b by 2 the whole square, and which is of one sign, right, because it's a square, so it's always positive. So that's the idea here. Okay, so I have chosen my next term to be x k plus 1 itself, and such that my error is now of the order x minus a plus b by 2 whole square integral x of this. So my error now is e is equal to f2, that is the second order derivative at some eta, divided by 2 factorial, which is 2 integral x minus a plus b by 2 the whole square dx between the limits a to b. Okay, so that's the idea. So what did we do? So that's an example of the two choices of size. Okay. So we started with a polynomial approximation, which is we choose to be a 0th order polynomial, that is, a function is evaluated only at x0. So first we chose x0 to be a, and then the integral is simply f of a into right. So in this case the integral is approximated to be f of a into b minus a. So that's what we call the rectangular rule, and then we had in that rule we had the error is of this form, right. That is the first derivative multiplied by x minus a dx, that is we get it as x minus a whole square by 2 between the limits a to b, that is b minus a whole square by 2. That is the error. The error will be here b minus f of f prime, the first derivative multiplied by b minus a whole square by 2. Okay, so that is the first rule, and then we choose the next case, we choose a different point as x0, still with the same polynomial p0 of x. Okay, so we choose the integral to be integral of p0 of x, but x is now chosen that the tabulated point is now a plus b by 2, and then the integral is simply f of a plus b by 2 by 2, that is f of a plus b by 2 into b minus a, but the error now is this coefficient multiplied by x minus a plus b by 2 dx, but this integral is 0 because it's symmetric, okay, and it's plus on one half and minus in the other half. It changes sign, it is not a 1 sign, it changes sign, so it's 0. So we said okay, then in that case what we can do is we can use this property, that to make psi of k of 1 sign, like to make psi of k 1 sign we add one more point, that is xk plus 1 now, okay, and then that is then we get psi of k plus 1 as x of x minus a plus b by 2 into x minus xk plus 1, and then the integral of that would be the error in this case, and that turns out to be the next order. So f of 2 eta, this is second derivative of the function multiplied by x minus a plus b by 2 whole square dx. Okay, so that's the next error. So that is we get it as b minus a whole cube by 24. So that's called the midpoint rule. So we call it as m. So that's the case. So midpoint rule is so we can see the error here. So midpoint rule in this particular function case it seems to be better in the sense that it is approximating the area in this case between this of this curve from this point to this point by a box of this shape, that is, so it's better than using the case of the rectangular rule where we had approximated it by a box here. Okay, so this is a much less error, okay, and that will obviously depend on the derivative of this function and the type of the function, etc. So it's not a general scheme, but in this particular example we see that the midpoint rule is better than the rectangular rule. Okay, so there are other cases which we should look at. Okay, so we could now consider a slightly higher order polynomial. Okay, so far we had taken p equal to 0. So now we look at p equal to 1, k equal to 1 case. Right. So we will then approximate the function by p1 of x, and then the error is x minus x0 into x minus x1. Right. That will be the error. So the first order polynomial. So here the psi 1 of x now will be x minus x0 into x minus x1. Okay, so then so p1 of x is now f of x0 plus f of x0 x1 x minus x0, and this error here x0 x1 x into psi 1 of x. Okay, so that's the way we are going to use how this define this error. So now again we will choose x0 to be a and x1 equal to b, and then we can compute that. Okay, so now we are doing a slightly better job of this polynomial. So we are doing the polynomial approximation here. So now we have done so far only p0 of x. Okay, now we are going to do p1 of x and then write the integral in this form. Okay, so let's look at that. So we are going to write our integral I of f is now as approximated by I of p1 of x, right, and and we are going to write p1 of x as f of x0 plus f of x0 x1 into x minus x0, right. So that's a p of p1 of x. So that the integral would be now I of f would be then integral a to b f of x0 plus f of x0 f square brackets x0 x1 x minus x0 dx. Okay, that is what our aim would be, and the error then would be in this particular case. So, we are saying that we will have now to compute the error will be the next term. So, we will approximate the error by integral f of x0 x1 x into x minus x0 into x minus x1 dx between the limits a to b. That is what the error is, and that is what we call psi 1 of x, right. So, that is and then we will have to look at the cases. So, a to b f of x0 x1 x into psi 1 of x dx. Now, we are going to you can do that thing, and we are going to choose x0 to be a and x1 to be b. So, we have 2 points. So, now we are going to evaluate the function value at both a and b, okay, 2 values. Okay, so, we are going to evaluate the function value there, okay, that will f of b and f of a, okay, and then we are going to compute this integral of this. Okay, that's the next point, and that's what we would call the trapezoidal rule, okay, and we will see this. But you can compute this, and you can see what the error would be, okay, and what's the nature of psi 1 of x is, okay, what is the integral psi 1 of x is. So psi 1 of x is, now remember, psi 1 of x in this particular case is x minus a into x minus b, okay. Now, the integral of that between the limits a to b is what we have to find. So, we look at in the next class this particular case, and also the graphical representation of this particular rule, which we are going to see, that is by choosing a polynomial of order 1 now, and choosing x0 to be a and x1 to be b, okay, 2 points, and then look at this case. So, in all these cases which we have discussed so far, we have made clever choices of x0 and x1. We are not choosing an x0 and x1 arbitrarily anywhere in between. We have chosen the case where x0 was for 0th order polynomial, and we choose x0 to be a and x0 to be a plus b by 2, the 2 cases. And now we are looking at the first order polynomial where x0 is a and x1 is b. Okay, so now we will evaluate the error in this and look at and compare these 3 methods in the next class.